Hello and welcome. This is Cambridge O Levels Chemistry Paper 4, Alternative Practical. Subject code is 5070. This is May-June 2022 exam, and this is variant 1 of this exam. Let's start. First question. It says, a student transfer 4 centimeter cube of aqueous potassium manganate from the burette to apparatus A. Name the apparatus A. So in the figure, we can see that we have a burette. So we have a burette, and from the burette, the student is transferring 4 centimeter cube of potassium manganate to a apparatus that is A. So this apparatus is actually a conical flask. Name the apparatus, just write conical flask. Next, part B, it says the student adds 25 centimeter cube of dilute sulfuric acid to apparatus A. Name a suitable piece of apparatus to measure 25 centimeter cube of acid. So for measuring acid, measuring cylinder is a best choice for the apparatus. So it is a measuring cylinder. Okay. Then part C, it says the student heats the mixture in apparatus A until it reaches 60 degrees centigrade. It says name a suitable piece of apparatus to measure the temperature. Thermometer. So just we have to measure, you have to measure it using a thermometer. Okay. So next, moving ahead, part D, it says a student. First bullet point, places apparatus A containing a hot mixture on a white tile. Then it says adds 10 centimeter cube of aqueous glucose to apparatus A, starts the stopwatch, stirs the content of A and records the temperature, stops the stopwatch when color changes, record the time taken. The student does this experiment at 5 different temperatures. The results are shown in the table. So on the left hand side, we have temperature in degrees centigrade, and on the right hand side in the table, we have time taken in seconds. So the temperature 55 degrees centigrade, 40, 32, 23, 20, and the corresponding times are 5, 25, 48, 90, and 150 seconds. So moving ahead, it says a grid plot is shown, a grid plot, the results is shown. So there is a plot or a grid of uh, is shown, and then and we have to basically plot these results. And in the plot, we have to first of all label the axes on the grid, include the appropriate units, plot the results on the grid, draw a curve of best fit. Okay. So now what we have to see, that the temperature is from 20 to 55 degrees centigrade and time taken is from 5 to 150. So we can see that on the x-axis, that is aligning with the temperature side. So we can label x-axis as temperature and degree centigrade, and on the y-axis we can label as time, time taken, and this is measured in seconds. And now we have to basically plot these values. So first value is 55 degrees centigrade, and the temperature or the time taken is 5 seconds. So with 5 seconds, we have 1, 2, 3, 4, 5. So almost 4 seconds is 1. So it is somewhere here. Okay. This is our first plot, first point. Then we have 40 degrees centigrade and 25. 40 degrees centigrade and 25. So it will be somewhere here. Okay. Oh, my first spot is gone. So let me draw it here. And then at 40, I have to draw it at 25. Not here, a little bit above. Then at 32 degrees centigrade, the time taken is 48. So at 32, so the time taken is 48, 44 and 48. So somewhere here is, so then we have 23 and time taken is 90. So 23 and time taken is somewhere here. 1, 2, and 3. This is 23. And then we have 20 and 150. 20 and 150. So these are our spots. So this, so we have, first of all, we have to label the axis. We have labeled the axis. Then we have to plot the results on the grid. So we have plotted the results on the grid. Then we have to draw the best fit curve. So remember, make sure that when you are drawing the best fit curve, I mean, excuse my digital drawing, you have to uh, make sure that most of these points fall on the line, and the overall curve or the overall linking of these points is a good one. So let me try to change, if I can change the color. Let's see, I can draw it with blue. Oh, sorry, green. So for example, if I'm going to draw it like this, uh, so I would just request you to excuse my drawings. That is not uh, a good way to draw this curve over here. But again, my recommendations is to make sure that you practice this in a better manner so that you have a fit line like that. So once you draw the curve, then it says that determine the time taken at 25 degrees centigrade, extend your curve to fit, extend your curve to best fit the determined temperature at which the reaction takes 180 centigrade. Okay, so at 180 degrees centigrade, so it would be something like this. Okay, so if I'm coming from here, the slope is a little something like this. Okay, so this is if I'm going to extend it. So at 180 degrees centigrade, it would cut somewhere here. So across here, we can say that it is something either 18 or 19-ish. Then it's a you have to find out what is the temperature at 25. So at 25 we'll have something around this. So this is 1 2 3 1 2 3. So almost at third point we will be having this cut, or uh, you can say between 3 and 4. So it will be something between 72 and 76 degrees centigrade for 25. So let's see. So just the time, determine the time taken at 25 degrees centigrade. So anything, so it would be 72 degrees centigrade for me. And again, it's same as is given in the marking scheme. And then at 180, we can say that the temperature is something between 18 or 19 degrees centigrade. So the marking scheme says 90 or 20, you can say. Marking scheme says it's 20. So I mean 19 is a good choice of answer. Then it says suggest why this experiment at 70 degrees centigrade is not done. So for example, at 70 degrees centigrade, if I'm going to have this run this experiment at 70 degrees centigrade, the time taken by this experiment, if we are going to extrapolate this curve, it would be way less than 5 seconds, and that would be uh, very short for a human or a or a person or a student to measure it. So just some suggestion, it would be the time taken for reaction to occur is too short to measure. Okay, so this is how you go about this question. So moving ahead, it says a student has a mixture of solid ionic compounds. The student adds the mixture to a beaker with water and stirs the content of the beaker. The beaker contains a colorless solution and an insoluble black solid. Okay. Draw a diagram to show how the student prepares the colorless solution. Sorry, how the student separates the colorless solution from the black solid. Label the practice the black solid and the colorless solution in your diagram. Okay, so we have to basically separate a solution. So we take a filtering funnel. This is something like this, and we take glass beaker or a measuring cylinder. Say, for example, it's something like this. And let me change the color. Take red. So we wrap the inside of this funnel with a filter paper. So let this red thing inside this is my filter paper. Let's label it. So this is a filtering funnel. This is your beaker. Um, this solution is colorless solution, and you should also have, so let me draw it with say a blue color, another say that is pouring this liquid into it. Um, and let me draw the black solid with this black thing. So this is your black solid. Okay. Um, so this is how it would look like. So student adds a mixture of ionic compounds into mixture to a beaker with water and stirs the content of the beaker. The beaker contains colorless solution and insoluble uh, black solid. So there is some sort of insoluble black solid. This is also black solid. Uh, then we have to basically filter this from the solution. So this is how the diagram should or will look like. Okay. So moving ahead, so in this question, it says the student tests the colorless solution shown in the table. Complete the table. First thing is name the gas formed and describe the test used to identify the gas. The first test is add dilute hydrochloric acid followed by aqueous barium chloride. The conclusions, so we have to find out the observation. It says the mixture contains sulfate ions and carbonate ions. Remember, if we have carbonate ions, the observation will be effervescence producing or bubbling of carbon dioxide gas, and the gas basically turns lime water milky, and a white precipitate is formed that also that will basically be telling us about the presence of sulfate ions. So first thing, so what would be the observations? Effervescence is produced or you can say bubbling is observed. Then you can say the gas turns lime water milky. So this is or will be the case for either for the acid reacting with the uh, carbon or the showing the reaction showing the presence of carbonate ions. And when we add aqueous barium chloride, so barium sulfate will be formed, and technically there will be a chloride solution. So uh, this is will be there will be a white precipitate is formed. So this white precipitate will be showing the presence of sulfate ions, and for the carbonate ions we have this effervescence and bubbling is observed that and the gas turns lime water milky. So the conclusion one is the presence one conclusion is given. The second conclusion is that carbon dioxide or CO2 gas is produced. Okay, so moving ahead, it's in part 2. It says aqueous sodium hydroxide. Add aqueous sodium hydroxide and warm the mixture. One of the observation one of the conclusions is that the mixture contains ammonium ions. So with the presence of ammonium ions, remember that ammonia gas will be produced. So ammonium ions in presence of aqueous sodium hydroxide will result in production of ammonia gas. So we can simply write as ammonia gas is produced. So now we have to write down the test for this gas. So basically it says first observation will be gas is produced with pungent smell, pungent or irritating smell. And the second thing is, since this is an ammonia gas, and it will turn the damped red litmus paper blue. The gas turns damped red litmus paper blue. Okay, so this will how we'll write this thing. Then it says add dilute nitric acid followed by silver nitrate. So we are adding basically HNO3, and then we are adding AgNO3. Okay. So what is happening here? So a pale yellow precipitate is formed. So the yellow precipitate is generally of iodides. Uh, so for this case, if we have a silver nitride, the yellow precipitate will be of, for example, silver iodide. So silver iodide will have a yellow precipitate, and this is actually a test for any, for example, sodium salt or yes. So for example, sodium nitrate. If we have a sodium nitrate, this will give something result like this. But we also remember that what we are talking about, we are talking about a colorless solution with some black uh, insoluble salt in it. So we are also adding nitric acid to this. So with the nitric acid, remember we are having sulfate ions and we are also having carbonate ions. So the carbonate ions, the presence was confirmed. So the carbonate ions again. So what will happen? The presence of carbon dioxide is there. So what we can simply say that the effervescence occurs, and the gas turns lime water milky. Okay, so the carbonate ion is there, so with the acid that reacts with like. Then a pale yellow precipitate is formed. So this is actually the presence, you can say, of bromine gas as well. So here, so for first conclusion will be, for example, CO2 gas is produced. Uh, and for the second part, AgI, no, sorry, not, it's not, it is the presence of iodine. So uh, presence of dyed salt, that is sodium iodide, is confirmed. So this is the reason for this, or when we have a yellow precipitate, this basically shows that this happens. Or what will happen with this reaction, that in, for example, if you have, oh, sorry, if you have sodium iodide, if you have, for example, sodium iodide salt, it will react with AgNO3 to form sodium nitrate plus AgI. I mean, I'm not balancing it, but this is some. So all nitrates are soluble, so nitrate will be soluble, and this will be, or AgI, or the silver iodide, is actually a yellow precipitate, and this happens in a acidic environment, and this actually is a test for checking the presence of sodium based salts. So moving ahead, use the conclusions from test 2 and 3 to name the ionic compound in the mixture. So test 2 and 3. So with test 2, we can say that we have NH4 positive, or ammonium ions, and here we can see that we have iodide ions. So a good choice will be to have ammonium iodide as the ionic compound in the mixture. So ammonium iodide, or NH4I. Okay, so this is how this or solution will look like. Then it part C says the student tests the insoluble black solid as shown in the table. So test one, he puts the black solid into dilute sulfuric acid and warms the mixture. The solid dissolves and a blue solution is formed. So remember, blue solution is always copper sulfate, and it's very poisonous in nature. So black solid, in terms of, so some X solid plus, you can say H2SO4, is giving, is actually dissolves in it and gives you a blue solution, plus something else. So this is actually the copper sulfate solution, and the color is blue because of the presence of copper sulfate. And we have to identify this X. So what we can say about this X is that the black solid contains copper ions, say Cu2 positive ions, and it can be any oxide of copper. So just write it that way. The black solid contains Cu2 positive ions or copper ions. The solid can be CuO, or you can call it as copper to oxide. Okay, so this is how we can say about this black solid. Then in part 2, it says some of the blue solution from test 1, add aqueous sodium hydroxide drop by drop until it is in excess. So for example, if it is copper sulfate, you're adding sodium hydroxide, NaOH. Okay, so you are adding NaOH. A blue precipitate is formed, which is insoluble in excess. So precipitate. So with this reaction, actually, you get sodium sulfate um, and copper hydroxide, and that is the blue precipitate. Um, and that basically confirms the presence of copper oxide. So you can say that no, sodium hydroxide. No, so this is not. So sodium hydroxide basically, when you start adding sodium hydroxide, it will be eating up the sulfuric acid that was present in the solution, and then when the sulfuric acid was totally eaten up, the copper sulfate or the blue precipitate of copper sulfate dies down, and that copper sulfate is actually not soluble, um, or is insoluble in sodium hydroxide. So that would be the case. So it basically confirms the the black solid contains copper ions, or actually Cu2 plus, and the black solid is actually an oxide, copper oxide, or copper to oxide. So remember what is happening here. So this jar basically contains copper sulfate solution, okay, and some dilute sulfuric acid, okay, plus some dilute sulfuric acid. So when you are adding sodium hydroxide, so the sodium hydroxide will be reacting with H2SO4. It is basically the acid plus base reaction. So it will be forming sodium hydroxide and water. And what we'll see is that the precipitate for copper sulfate, which is blue in color, copper sulfate is actually insoluble in sodium hydroxide. So it will not dissolve, it will settle down. And when we have excess sodium hydroxide, the no copper sulfate will be dissolving in that. So that basically confirms that we have copper 2 positive ions in the solution. Then to some of the blue solution in test 1, add aqueous ammonium drop by drop until it is in excess. So copper sulfate plus aqueous ammonia. So now if we are going to add copper sulfate in aqueous ammonia, what will happen that this copper sulfate actually dissolves in aqueous ammonia. So copper sulfate plus ammonium hydroxide, that will give us a copper precipitate, or a dark blue or a dark blue solution sort of thing forms, and that is actually a complex tetraamine copper sort of an ion. So what we can write that a light blue precipitate is formed. The precipitate dissolves in excess. Uh, uh, Dark bluish solution remains. And this dark blue solution, this dark blue color is actually because of complex ion, which we call as tetraamine copper. Okay, so basically this is a test of copper. So it's a tetraamine copper that basically generates this dark blue color that is different from the insoluble copper sulfate precipitate, which was insoluble in sodium hydroxide earlier. So this is how this whole thing goes. So moving ahead, question number 3, it says the student has 3 colorless organic liquids W, X, and Y. One is alkene, one is alcohol, and one is carboxylic acid. But the student does not know which liquid is which. So describe a series of tests to determine which liquid W, X, or Y is alkene, which is alcohol, and which is carboxylic acid. Each liquid must be identified by a positive test. You are provided with separate samples of W, X, and Y, acidified potassium manganate, aqueous bromine, solid calcium carbonate, an apparatus normally found in a school laboratory. Okay, so now we have to basically describe these tests. We have to provide a detailed description. Uh, so in our detailed description, we can say that let W is an alkene, X is you can call as alcohol, Y is carboxylic acid. So, so this is be like this. So if we are going to test for sample W, um, you can always say let. For the examiner, you can always say let like this. So for sample W, you can say take a small volume in a test tube, add few drops of aqueous, sorry, bromine, uh, aqueous bromine. Okay, you can also using a dropper. The color changes from orange to colorless. So for the test for an alkene, from orange to colorless. Okay, so this basically the presence of alkene is so sample W is an alkene. Okay, so again remember that aqueous bromine and all this alkenes and things, it's always better to wear a face shield or face mask because bromine gas is very detrimental to health if breathe. So for precautions, use nitrile gloves and face shield while handling um, the bromine gas, or bromine is toxic and corrosive. I mean, this is just toxic. Then for, you can say, sample X. So for X, assuming that it's an alcohol, uh, we can use aqueous potassium manganate solution to test, and the color change from purple to colorless. So for an alcohol, again, same, take a small sample, volume in a test tube, add aqueous, add acidified, acidified aqueous, oh, spellings, aqueous potassium 7 manganate solution. Again, using a dropper, the color changes from purple to colorless. From purple to colorless. So again, you are actually handling potassium permanganate, that is an oxidizing agent. Similarly, actually a strong oxidizing agent, and then you are also handling alcohol. So it's always good to wear gloves and avoid contact with skin for the oxidizing agent. Wear gloves and avoid contact with skin for KMNO4, potassium permanganate. Okay, oxidizing agent. It is actually a strong oxidizing agent, to be very exact. Then we have sample Y. So for sample Y, this is a carboxylic acid. So the simple test is take a small volume, add solid calcium carbonate, and this is an acid. Effervescence is produced, and carbon dioxide gas will be there. So again, take a small sample in a test tube, add solid calcium carbonate. So if it's an carboxylic acid, effervescence slash bubbling of a gas is observed. The gas turns lime water milky. So The protection terms again, so you're using acids, so it's better to wear gloves. So use slash wear gloves to handle the acid, the carboxylic acid. So these are, or in this way, you can describe the test for these three samples you have. Okay. So moving ahead, question number 4. Question number 4 says a student determines the concentration of aqueous sodium hydroxide, uh, NaOH by titration with aqueous citric acid. The student follows the following steps. Step 1, record the mass of empty beaker and then add solid citric acid. Step 2, records mass of beaker and citric acid. Step 3, add distilled water to the beaker and stir the mixture until the citric acid dissolves. Step 4, transfer all the aqueous citric acid from the beaker into a 250 centimeter cube volumetric flask. Step 5, fills the volumetric flask up to the mark with distilled water and shakes the flask to make solution P. So now remember, so now this is our solution P. Step 6 uses a measuring cylinder to add 25 centimeter cube of solution P into the conical flask. Step 7, add a few drops of indicator to the flask. Step 8, fills the burette with aqueous sodium hydroxide and records the initial volume in the burette. Step 9, add sodium hydroxide to the flask until indicator changes color and records the final volume of the burette. The student repeats the steps 6, 7, 8, and 9 3 more times. Okay, so basically he's performing titration reaction. So part A, the student uses incorrect piece of apparatus to measure the volume. Identify the incorrect piece of apparatus and suggest a more accurate piece of apparatus. So incorrect piece of measuring is the measuring cylinder. So here uh, uses a measuring cylinder to add 25. So the good is to use a pipette. Mhm. So incorrect piece of apparatus is measuring cylinder, and more accurate piece is pipette. Then part B, it says explain why the contents of volumetric flask are shaken in step 5. So shaking results in formation of a homogeneous solution. The concentration becomes uniform. Okay. Then part C, it says explain why indicator is needed in step 9. So indicator is needed to check for or to identify for the when the reaction or when the titration reaction is complete. So where the indicator is needed to identify the completion of the titration reaction. Okay. Then at part B, it says the diagram shows the masses on the electronic balance. Calculate the mass of citric acid. So without the mass or without adding citric acid, the mass is 45.36, and with citric acid, it is 50.32. So the mass actually is the difference of these two values, 50.32 minus 45.36. If we do the calculation, it becomes 4.96 grams. 4.96 is our answer. Then in part E, it says calculate the number of moles of citric acid in the beaker. MR is given, so number of moles is equal to mass in grams over MR. So mass in grams is 4.96. That is divided by 192. And the value comes out to be, so this value is actually 0.25, sorry, this is 0.0258333 and so on. The good is to use three significant figures, so 0.0258 moles is a good answer. Then it says calculate the concentration in mole per decimeter cube of citric acid in the volumetric flask. So these are actually the number of moles in 250 centimeter cube. So this actual concentration is 0.0258 moles in 250 centimeter cube of the solution in the volumetric flask. So remember, 1000 centimeter cube is equal to 1 decimeter cube. So mole per decimeter cube. So if we have to multiply, so we have to find out the concentration. So just simply multiply top and bottom by 4. So multiplying bottom with 4, it will become 1000, or well, the first step will be 250 into 4. And this comes out to be 0.103333, so on. So the good is 0.103. 0.103 or 3 decimal places mole per decimeter cube. This is the concentration we have. Then part G, it says the diagram shows part of burette with liquid levels at the beginning and end of titration 1. Okay, so use the diagrams to enter values of titration 1 in the results table shown. Final value of burette, that is 35.7 centimeter cube. Initial value is 4.22, and value of sodium hydrochloride added. This one was the difference of these two. So the difference of these two is 31.5 centimeter cube. Then part B, best titration results. So remember, the best titration results are the ones which are the most close by. If we see that the 30.9, 30.7, 30.8 are very close by, the difference is 0.1, whereas 31.5 in titration 1 is an outlier. So the best results, we can say that these three are the best results we have. Then in part H, the table shows the results of 3 titrations. Other 3 complete the table by taking the best titration results. So we have already taken them. Then it says explain why you have taken these values. So the all values in 2, 3, 4 are close to each other. That is around between 0.2 centimeter cubes. The values of titration results 2, 3, and are close to each other, whereas titration 1 seems an outlier result. Okay. Then it says use the best titration results to calculate the average volume of sodium hydroxide used. So best titration, so we have 3 results. So the volume used. So we have 30.7 plus 30.8 plus 30.9 divided by 3, it comes out to be 30.8 centimeter cube. So we'll go with 30.8 centimeter cube. So in from your answer in F, calculate the number of moles of citric acid in 25 centimeter cube of P. So remember, the concentration of P is 0.103 moles per decimeter cube. So this is the concentration we calculated, decimeter cube. So we have to basically uh, calculate the number of moles of citric acid in 25 centimeter cube of solution P. So 1000 centimeter cube has 0.103 moles. 1 centimeter cube will have 0.103 divided by 1000 moles, and 25 centimeter cube will have 0.103 divided by 1000 into 25. This comes out to be 0.00258 moles. So 0.00258 moles is the right answer we have. Then part K, it says the equation for the reaction between citric acid and sodium hydroxide is shown. Calculate the number of moles of sodium hydroxide that will react with citric acid in 25 centimeter cube of solution P. So I have as 1 mole of citric acid reacts with 3 moles of sodium hydroxide. And actually we in the reaction we have 0.02, so 0.00258 moles which are reacting. So let's calculate the moles of, so 1 mole of citric acid reacts with 3 moles of NaOH. So we have 0.00258 moles of citric acid. They will react with 3 multiplied by 0.00258 moles of NaOH. So if we are going to do multiplication like that, that will give us 0.00774 moles of. Then it says calculate the concentration in mole per decimeter cube of sodium hydroxide. So remember, so the number of moles of sodium hydroxide that are used are 0.00774 moles, and volume of sodium hydroxide used is 30.8 centimeter cube. So then concentration is equal to 0.00774 moles per 30.8 centimeter cube. So this is the concentration. So we have to calculate concentration in mole per decimeter cube. So that is, you can solve it like this: 30.8 centimeter cube have 0.00774 moles. 1 centimeter cube will have 0.00774 divided by 30.8 moles, and 1000 centimeter cube, that is actually 1 decimeter cube, will have 0.00774 divided by 30.8 multiplied by 1000, and this will be the number of moles we have. So per decimeter cube, and this comes out to be 0.251 moles per decimeter cube. Okay. So now it says that 25 centimeter cube of sodium hydroxide is added to an excess iron sulfate. So it means that sodium hydroxide is the limiting reactant. The equation shown, so 2 moles reacts with 1 mole of ferrous sulfate gives us thing. So a precipitate is formed. So from in the equation and from your answer in last part, the part L, that gives us the concentration of sodium hydroxide. So the concentration is 0.251 mole per decimeter cube. Calculate the number of moles of iron hydroxide, that is the precipitate. So remember, this is the precipitate is made. If you don't have the concentration, so we'll use this concentration. So this concentration. So from the equation, we can see that 2 moles of NaOH, 1 mole of iron hydroxide. So 1 mole of oxide will give you half mole of iron oxide. So we have so number of moles. So we have to calculate number of moles of NaOH used. So number of mole used is, so the volume is, so we actually 0.251 moles in 1000 centimeter cube, and we have used only 25 centimeter cube. So the total number of moles that are used are 0.00628 moles. So these are the moles of sodium hydroxide that are used. So these many moles will produce half of the moles. So number of moles of iron hydroxide, it will be 1/2 of NaOH that are actually used. So the number of moles of NaOH and sodium hydroxide used 1/2 multiplied by 1.00628, and this comes out to be 0.00314. 0.00314 moles that are used. Then it says state the color of the precipitate. So color of the precipitate, remember this is an iron. Iron has 2 precipitates, iron 2 positive and iron 3 positive. So 2 positive are the green ones and iron 3 positives are the reddish brown ones. Reddish brown ones. So this is iron 2 precipitate. The precipitate is green precipitate. So green precipitate. State of iron hydroxide because of Fe 2 positive ions. This is the reason, just because of your information, but just simply if you're going to write as green precipitate, that will be enough and you'll be getting complete credit for this equation. Last question, question number 5. It says the student measures 25 centimeter cube of 1 mole per decimeter cube of hydrochloric acid into a glass beaker. Then it measures the temperature of the hydrochloric acid. Then it adds 30 centimeter cube of excess sodium, excess aqueous potassium hydroxide. And part 4 records the maximum temperature of the mixture as it reaches. So initial temperature is given to us, that is 19 degree, final temperature is 20 degree. So use the diagram table below. Initial temperature 19 degrees centigrade, final temperature 28 degrees centigrade, change in temperature 19 minus 28, or that is 9 degrees centigrade. So 28 minus 19 is 9 degrees centigrade. Use the information in the table in A, such as the type of reaction taking place. The acid plus base, actually it is acid plus base, salt plus water, titration reaction, or an exothermic reaction. So it is a titration reaction slash this is also an exothermic reaction. So from the says from the reaction taking place, information in table 1. So table 1 that there is a change in temperature. So the better suited is to write exothermic over here. So then it says the student repeats the experiment using 2 mole per dm cube instead of 1 mole per dm cube. So actually twice the concentration of hydrochloric acid is used. The volumes are kept constant. The aqueous potassium hydroxide is still in excess. So the base is in excess. So the excess base is there. Predict the change in temperature. So more acid you will be using, but potassium hydroxide is still in excess. So more will be the rise in temperature. So twice the concentration. So we predict that there will be twice the change in temperature. So 18 degrees centigrade. Reason the concentration reason is the concentration of the acid doubles while keeping the base in excess. The more energy will be released. Double the shall be least, making double the rise in temperature. Okay, something like this will be a good answer to this point. Then it says this temperature change measured is lower than expected. Suggest a reason for the temperature change being lower because of heat absorption and heat loss. Heat absorption equipment and heat loss. Suggest an improvement to the experiment which will make Mayer temperature closest to use, for example, insulated beaker. So are they using a beaker? Say, let's say glass beaker. Yes. So insulated glass beaker. Use insulated glass beaker. Okay. So this is how you can answer this question. So this is the last question for this exam. Again, so I wish you best of luck for your upcoming chemistry exam. And thank you all for listening. If you have any questions, please feel free to write in the comment box of this video. And again, all the best for your future endeavors. Thank you.